never mind what kind of processing, ADC or DAC, the final goal is to reconstruct the signal as close to the original as possible. So how to judge, how to assess the correctness of the DAC or ADC? Allow me to show you. Oh, not yet. Okay, anyway. Why we would like to do such kind of digitization? Simply because after digitization in digital domain, we get more flexibility. It is easier to upgrade the system. You can control the accuracy just like how many bits you would like to have. 16 bits, if it is not enough. Right now we have oversampling, right? Sigma delta delta sigma converter to make the overall effective number of bits more than 20. Okay? But how can you make it? Okay, we will explain. All right? And it is even easier to reproduce the overall system, even in different processes. All right? Yeah. Anyway, all right. Finally, how to test the correctness, the performance of the overall system. For example, for our mobile phone, right? If you call somebody, first of all, we need to digitize, right? Because everything inside the mobile phone, I mean for baseband, okay, that is a very important idea. For baseband, almost fully in digital. Okay, but in natural domain, your vision, your listening, even your sensing of your body, everything is in analog domain, right? So baseband DC, natural domain, digital, sorry, natural domain, analog. So allow me to show you the most easy to understand example audio. If you would like to call somebody, right, then from the beginning, our voice needs to be recorded. I mean, we need the help of ADC to digitize our voice for further processing. When you need to process it, you cannot transmit your original voice data. Why? Too much. The spectrum for 3G, 4G, or even 5G is really, really expensive. So we need to share the bandwidth with thousands of users in the same zone, right? So everybody can only get a very limited bandwidth for voice transmission. So we need a lot of compression. How can you make it? And also to the air, not only the callee, 你要打电话的那个人, he or she can get the signal. Even the hacker, they can, because it is wireless, right? They can use some kind of antenna to receive your voice. Then you will know what you are talking about, especially if you are some kind of prime minister, right? Or the president, blah, blah, blah. USA agent in the past, years ago, they monitor everybody on Earth, not only Putin. Or maybe they don't have the chance to monitor Xi Jinping. That is the real emperor on Earth right now. Yeah. But for all the other, maybe Putin is also impossible, but for all the leaders in democratic world, everybody was monitored by US agency. Yeah, it doesn't make any sense. So how to protect yourself? We need some kind of encryption, 加密. So we need not only compression, 压缩, but also encryption, 加密. Okay? Yeah. Anyway, that is what we need to digitize. Can you do such kind of compression and encryption in analog domain? I cannot say it is impossible, but almost impossible. Okay? Too hard. Anyway, so from the very beginning, we need to convert the voice into some kind of electrical signal. So we need help of this microphone. Okay? to convert the vibration of the air into voltage or current. Then we need to do, voice to electrical signal. Then amplification, and then ADC, right? Okay. Then the outcome will be in digital domain. And you can do everything as you like. Compression, encryption, low-pass filtering. Oh, from the very beginning, they need 8th order low-pass filtering. Is it easy to realize in analog domain? No. According to device mismatching, forget about it. For analog domain, I guess 2nd order good enough. How about 3 or 4? Forget about it. You will get too much mismatch to destroy the filtering property. Okay? So it is only possible in digital domain, because in digital domain, everything is perfect. Everything is ideal. You can do anything as you like. But the more order means what? The more computation time it needs to take. But anyway, right now we have 8 core, 10 core, 20 cores, as you like. All right. So we have more than good enough computation power from our smartphone. You can do much better, filtering, compression, encryption. Okay. Yeah. After that, you can transmit your digital content through the air to your colleague. But for such kind of digital communication, you need to be very careful. For any kind of communication, usually we don't transmit the real digital content to the air or even on the bus. Okay, for your USB, no. Never mention about for your mobile phone. Okay, digital communication only means the content is digital. But how about the physical signal, RF signal, fully in analog? Okay, if you transmit 1 and 0 directly into the air, again, according to Taylor's expansion, wow, you will have a lot of harmonics. For example, if you transmit at 1 gigahertz, then second 2G, 3G, 4, oh wow. You will destroy all the other transmitters in the air, interference with each other. It doesn't make any sense. Nothing is allowed. Very close to pure sine wave is required for such kind of even digital communication. Okay? But what is the content? I still would like to transmit the 0 and the 1 through the air, right? For example, we have the so-called BPSK, binary phase shift keying, with the same sine wave, but 0 degrees for 0, 180 degrees for 1. That is the way we can transmit the digital content on analog sine wave. Okay, the same sine wave, 1 gigahertz, but with different phases. That's it. All right. So if you look at the spectrum, I cannot say, hey, look, it's still 1 gigahertz, no 2 gigahertz. Yeah, not that, but it is not a nice spectrum. According to such kind of modulation, it will spread a little bit. Okay, because you change the phases of the sine wave. Right? Even it is still 1 gigahertz, but you change from 0 to 180 degrees. If you have QPSK, then you have 4 phases. Right? It will spread a little bit wider. That's it. It depends on how much bandwidth you can get from the air. It is allowed from our NCC or any kind of agency. Yeah. Anyway, in each country, we have an organization to control such kind of bandwidth. Okay? In USA, FCC or something, I forgot. Yeah. Anyway, it doesn't hurt your 2G, 3G, or 4G, anything. Okay? Because we don't have such kind of harmonics. Too much for explanation. Yeah, let's go for this. Yeah, after we transmit the signal, the digital content on analog signal to the other side, then the callee will get it through its receiver, right? But the content is digital. How can your callee enjoy it? We need to convert signal back, reconstruct the signal back. So we need back digital to analog converter to become an electric signal. But you cannot enjoy the electric signal, the voltage or the current. You will be shocked, right? So we need to convert it back to audio vibration. So this is the reason why we need speaker. Okay? But they are equivalent to each other. To convert audio vibration to voltage or voltage barrier, in theory, they are exactly the same. Yeah. So, what do I mean? Even the speaker can become microphone. If you speak to the speaker, okay, and use oscilloscope to measure the two terminals, you will see your audio signal. That's it. Okay? It is much more efficient than the microphone inside, but it's too bulky. 它太大颗了. So usually speaker and, I mean in practice, speaker and microphone, they were separated. But in theory, they can be the same. All right, the same mechanism. Yeah. Anyway, after that, you get the voice output. So you can sense the difference to check the overall quality. Right? That's it. That's it. So in the past, how can you know for our cellular phone, how can you sense in Taipei City, in Los Angeles, in San Francisco, the overall quality is good enough? This is the city. They have all those equipment in the same car, right? Then they drive, such kind of full scan or full scanning around the city. Then to check, here is no good. Then they can call the base station company to change the antenna or the power or everything, okay? Or they need to install new base station in this area. Yeah, they can get a lot of money even for such kind of quality measurement. Okay, so once upon a time there was a professor, very smart at such kind of money making. So he got some kind of most project, to sponsor the luxury car, the equipment inside, and after that, his student needs to drive all the way to help his supervisor get a lot of money from the base station company. Wow. So the professor can live much happier than us. We teach our students, but get nothing from the industry, right? Anyway, for such kind of RF transmitter, how can you transmit the content? Never mind the voice or data or your line, your messenger, right? Originally, the information is in digital domain. Then after baseband processing, right? Compression around everything. We split the data into I and Q. For what? That is another very important idea for telecommunication. Because for each frequency in the past, for each channel, you can only carry one information, bit by bit. Okay? Yeah. But after humankind figure out, wow, sine and cosine, they are orthogonal. I mean, the phase difference is 90 degrees. So if you multiply sine by sine, you will get the original signal. But sine by cosine, because they are orthogonal to each other, you will get 0 after low-pass filtering. So it means what? You can transmit two data at the same time, okay? With the same carrier frequency. Wow, That is one with sine, the other with cosine. Okay, sine wave and cosine wave. They can carry BPSK or QPS, the so-called PSK, any kind of shift keying. Never mind frequency or amplitude, I don't care. You also have QAM, right? Amplitude multiplication, quadruple, 4 magnitudes, blah, blah, blah. Anyhow, yeah. So for any kind of telecommunication modulation, you can apply to sine and cosine configurations. You can transmit 2 bits at the same time. Okay, that is the brilliant idea for humankind. We can double the transmission speed. Oh, not the bit rate, bit per second, through such kind of I data and Q data. I means in phase, 同向. Q, quarter, right? So it means what? 90 degrees in difference, orthogonal, 正交, with the original one. That's it. Anyway, you still have data in digital domain. I told you already, everything in the air should be analog instead of digital, right? So you need such kind of DA converter, digital to analog converter. Then you can see 0 degree, 90 degrees. You have such kind of mixer. 混波器. So how can you make sure your mixers, we call it local oscillator, 本地振荡器, can generate 2 signals with exactly the same frequency but 90-degree difference in phases? Huh? You need help of another very important IP called lock loops. First of all, PLL. Phase lock loop, or DLL, delay lock loop, blah, blah, blah. Okay, so the most important IP actually is data converters. But second is lock loops. Hopefully, to the end of the semester, I can teach you both. Okay? Yeah. I hope I have the time to finish at least data converters and phase lock loops, PLL and DLL. Anyway. After separate modulation, then you can combine. You can sum them up. Never mind sine plus cosine to the air. But usually, to enhance the sensitivity, we don't convert the baseband signal all the way to radio frequency. No, the sensitivity will become too low. So usually we convert baseband to medium band. Then another mixer to help you push the medium band signal to radio frequency band. That is the usual case. Actually, we have the other so-called zero mid-band transmitter, but the price is either very hard to design or less sensitivity. That is really no good. Okay? For example, for our radio, FM radio, the mid band is usually 10.7 megahertz. So from your DC, your baseband, okay, for the first modulation to this one, and then to the final one. For example, ICRT, that is 100.7. So here, from medium band to high frequency band or to RF band, actually for ICRT it needs to be 90 megahertz for the second. Okay, so this one should be tunable. Because I don't think you always listen to ICRT, it doesn't make any sense. You need to tune it. Okay, how to tune it? Because the mid band is fixed. Okay, so you need to tune the oscillation frequency for the second local oscillator. All right, and how to make it? Again, PLL as a frequency synthesizer. 频率合成器. Okay, yeah, either PLL or DLL or both. Yeah. So allow me to show you this kind of YC system. You can see that is the layout. But allow me to show you some of the chip, DA and ADC, DEC, ADC, and also PL, blah, blah, blah. And this is humankind's dream to make the radio totally with software. That is so-called software radio. Does it still on Earth? Maybe not. Because nowadays, I think everything almost defeated by website audio, right? Just like I listen to BBC every day when I drive to my office or back home. I always listen to BBC, right? But how? Through web. So we don't need any kind of RF transmitter, AM transmitter. I think humankind will get rid of that in the near future. Okay, so maybe this one already passed away. But in the past, humankind would like, because we have a hardware tuner, right? So they hope they can implement everything in software. But anyway, you need a lot of ADC and DAC for help. Even for motor control, just like your DVD player, the Blu-ray VR, right? Blu-ray player, yeah. How to control the spinning, the rotation of your disc? Oh, you need a lot of accurate control. Now allow me to show you. Look, even to control the speed of the motor, you need a lot of ADC and maybe DAC. Okay, so this is from analog devices, a lot of chips for data converters to control accurate enough rotation for the motors. Yeah, or a lot of consumers electronics. I would like to tell you that if you take away the data converters, maybe nowadays nothing will be fine. Maybe even the fan, if it is some kind of DC electrical fan, you take away ADC, DAC, or PL, well, it will also be malfunctional or totally not function at all. Okay, so data converters, like loops, are really important for humankind's daily lives. That is the brief introduction to the brief introduction chapter. And right now, this is the main body for our brief introduction to data converter. I need to thank my very good friend, Professor Randall Geiger. Yeah, maybe in the past, I invited him to come back NTUST for intensive class, maybe once per 2 years biannual. But maybe I will invite him this year again. Yeah, hopefully he will have time. I need to thank him. So just like our traditional religion, we need to pay more respect. Bye. Anyway, kidding. This is the outline of, since after all those are from Professor Geiger. Anyway, I told you already, data converter is the most widely used IP on Earth. Yeah, it has many kind of different architectures, but how to design? Usually a challenge. Even for very experienced designers, it's really hard to design a good enough data converters. Okay? But even though there are quite many architectures, but most of them we used are quite simple. I think nowadays two major structures. SAR, first of all, and then pipeline. That's it. Forget all the others. Yeah, we still have flash ADC, but it is only used for very high frequency one. So for on-chip application, usually SAR first. If SAR cannot fit your need, then maybe pipeline. Okay, two major structures. But I told you already, yeah, it is some kind of major challenge even for experienced designers to meet the specifications. Okay, you need to consider not only the yield, the performance, but also the power. Yeah. For example, for IoT sensing, not this one. Okay. For IoT, actually, it is really hard to get power. Maybe we embed the battery with our IoT node, right? But how long the battery can run, it depends on how much power you consume. So in the past, humankind focused on this, microwatt. Nowadays, well, we focus even further into nanowatt domain, okay? Not only for sensors, but also for ADC. Wow, back. Nanowatt, what you can do, really, really limited, okay? Yeah. How many parameters you need to face for data converters? Wow, a lot of them. For example, nonlinearity. Yeah, and also you need to get good enough accuracy or linearity, you need to match critical devices on the chip, right? And how fast you can operate. And also you need to pay attention because it is strongly related to the parasitics of your layout. For my student, from presim to postsim, maybe more than 3 bits was lost. That is according to parasitics. So we need to try to figure out every kind of detail. Yeah. Which one? Because you have a lot of parasitics. You need to know which one or which ones cause the most damage. Then try to get rid of that. Okay, to reduce the parasitic or blah, blah, blah. It's some kind of hard work. It takes a lot of time. First of all, you need to know which one causes you the most damage, right? You need to guess, then check your layout to get this, the correct ones, then try to reduce it. Anyway, yeah. But even you make it for your post simulation, after application, you still need to test the real performance. Or it is another story. Sometimes it is even harder, yeah, than your design. I mean, for high-end data converters, it takes a much longer time. Yeah. So even to improve the resolution, effective resolution by only 1 bit is a major challenge. Hey, look, right now I design a 12-bit in effective number of bits. Can I make it become 13 or 14? Oh, it takes a very long time. Okay, even though you are very good at 12 bits already. How about 13? How about 14? Wow, maybe it takes you months or even more than 1 year to make it. And to not only the enough effective number of bits, to improve even a single performance parameter, just like linearity, INL, SNR, signal to noise ratio, or SINET, okay, signal to noise and some kind of distortion, spurious-free dynamic range, any one of them is a major challenge for you, okay? Yeah, and testing is really complicated for high bit, high resolution case, and the simulation time is more than you can imagine. It takes not only days for complicated cases, maybe weeks. After weeks, you can make one simulation. Wow, that is really, really challenging. Okay? How to improve the performance? Again, you need to identify many kind of small contributions and try to reduce the impact of such kind of small ones. Yeah, small and small and small altogether make a huge impact on your output, on your performance. So you need to study one by one, okay, enhance one by one. It takes, again, a much longer time than you expect, especially for new designers. Okay, let's go for it. Before design, you need to know every common sense, any kind of background knowledge. For AD converters, yeah, this is your input, this is your output, right? And usually, we have some kind of reference voltage. That is the usual case. And for something, it is the bus instead of 9. So it means a bus means multiple 9s in parallel. So from LSB D0 all the way to MSB Dn-1. Okay. Sometimes we have 2 references. It means your input will operate between these. Okay? And sometimes we have differential input. So, yeah. And again, both positive and negative input needs to be inside the positive and reference, positive and negative reference. Yeah, we have quite many expression, notation, or symbols. Sometimes look like this. From this to the output, okay, and that will be reversed. Usually for the digital output, it is represented in a minorly weighted formula. Okay, 用2进位的方式来表达 why we need for the final output it should be in such kind of minorly weighted structure, simply because the information density is the highest for our current digital domain. Okay, because for our digital domain we have only 0 and 1. Yeah, for such kind of minorly digital domain, minorly weighted structure is the best for information density. What does it mean? With the same information, you need the least bit to represent it. So that is the concept for the most information density. 资讯密度最高，就表示同样的资讯，你需要最少的位元数去代表它。That's it. But in digital domain, we have many kind of the other representation. For example, I mentioned already, one is called thermometer code, right? Yeah, it is also in digital domain because for each bit, it has only 0 and 1. But compared to such kind of minorly weighted structure, yeah, n bits here equivalent 2 to n's power. In such kind of thermometer representation, it doesn't make any sense. We wouldn't like to store thermometer code into our device because the information density is really bad, right? So again, for the same information, you need a lot of bits to represent it. It doesn't make any sense for storage. Okay, so for minorly weighted, 2进位权重视, it means each bit to the next, the weight will be doubled. And from D1 to D2 also doubled, right, all the way. That's it. So to the last, we call it, it carries the most weight, right? So we call it most significant bit. Okay. And how to characterize the performance of such kind of ideal ADC? Usually we talk about the linearity. The linearity means the static performance. Later I will explain. Okay? This is your analog input. After conversion, you get some kind of digital output. Right? That's it. That is the output code, digital code, compared to your original input. And you can see, again, this is some kind of stairwise characteristic curve, 阶梯状的特征曲线. And if it is ideal, you can see each stair look like the same. This, and that. Oh, they are all the same. Congratulations. Okay? Yeah, but in practice, oh, this is an idea. In practice, no, forget about it. Yeah. In practice, each stair will be different from the others. That is the ugly truth. After fabrication, you will get a lot of, how can I say, mismatch. Okay? According to process variation, blah, blah, blah. But what is the meaning for such kind of code? What is 0 means? What is 1 means? What is, oh, they have their representative value. Okay? So we call it, if you convert back, ideally, from the digital code to, for example, this is voltage, and you convert it back to voltage. So for such kind of representative value for your digital code, yeah, we have input voltage with tilde, okay, some kind of Greek letter or something, okay. That is the interpreted value of such kind of code. So hopefully, the real value for C1, this one, will be exactly the same as this. 2 here, 3 there, ideally. Okay? Yeah. But how about your input? Sorry for that. You cannot expect. You have only 1, 2, 3, 4, blah, 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 0, 0, all the way. You cannot expect you have only such kind of discrete input. No, sorry for that. Your input is analog. Analog means what? Infinite possibility. That's it. Oh, really sorry for that. Okay? I told you for quantization. I forgot to mention that. Usually we choose the closest quantization level to represent your input. But sometimes we choose, yeah, not the closest one. Okay? You can see from here to there, they are all represented by 0. Only if you cross over, you are larger than or equal to this one, then all the whole region will be represented by 1. The whole region by 2. Okay? Okay? That is another way for quantization. It is easier to realize, to be honest. Okay, but problem. You can see from here all the way to 1, less than 1 will be represented by 0. Oh, it means what? Even your input is 0.999 LSB. After quantization, it will still be 0. So what is the maximum error between your input and your output? Because this region were all coded as C0. So the maximum error is 1 LSB, very close to 1 LSB. Okay? Similar condition happens for the second. You can see from 1.0 to 1.999999 LSB. After quantization, all of them will become 1 LSB. There. So again, the maximum difference or the maximum error is almost 1 LSB. LSB means, in theory, the size of 1 step. Okay? And they are exactly the same in theory. Yeah. Anyhow, so this is your real input. And that is your digital output converted back to analog domain. They are not the same. No, I told you already. Okay, so epsilon means the quantization error. Okay, that's it. And I played the voice demonstration for you. You can listen to such kind of quantization error. It sounds like very much noise. So sometimes or always we call it quantization noise. Since after you see, we mention more frequently as quantization noise instead of quantization error. Okay? Yeah. Anyway, anyhow, I would like to tell you the reconstructed value and the real input, actually, they are usually not the same. There has some kind of error, quantization noise or quantization error. Okay? And also you can see the other definition is we call it transition point or break point. For the jumps of your input from 0 to 1, 1 to 2, 2 to 3, all those values to get jumps for your output code. We call it transition points or breakpoints. That is another good definition for the conversion curve. Ideally, all those transition points or breakpoints, they are evenly distributed along your input range. 这些东西会均匀的分布在理想当中，会均匀分布在你的输入轴。That's it. Okay. So you can see the mapping. For example, XT1 means C1, XT2 means C2. So XTK means the transition point, but to make the output code become CK. That's it. Okay, that is the definition. But if you subtract your representative analog value from your real input value, you will see, wow, the quantization error look like this. Even though this is ideal, you still get one LSB in error. Intuitively, it doesn't make any sense. Even though the ADC is ideal ADC means no error. Sorry for that. Under such kind of situation, even though you have ideal ADC, you still get maximally one LSB in error. Wow, it is hard to understand. Why? Ideal structure, ideal circuit still get such kind of very huge error. If you are unhappy, no worries. We can help you to minimize the error. Okay? By 50%. See? What you can do? Redefine your transition point here. Because the original transition point is 1 LSB, 2 LSB, 3 LSB, right? So the new transition points should become 0.5, 1.5, 2.5 all the way. Then congratulations. The error for perfect ADC is limited, bounded by half LSB. But it's still not zero. It's really upset. Okay? Anyhow. Right now, we are only concerned about the so-called linearity, but we still have a lot of parameters, to check whether or not your data converter is good enough. Okay? For the commercial data converters, they list, I guess, around 20 parameters. That's too much. To be honest, for our application-specific data converter, usually we focus on very few parameters. I guess, first of all, INL. Secondly, ENAP. INL is for static. Why we call it static? Because in theory, you can increase your input very slowly from the minimum to the maximum, very slowly. Okay, then you will get such kind of error result. That is the so-called INL. Okay, but non-linearity error, but why we call it integral? The other one is called differential. Yeah. Maybe not today, but anyway, in this chapter, I will explain such kind of difference later. Okay, today or 2 days later, because next week, don't come back here. Next week, that is the D-Day for your second homework. Please go to our computer room. Okay, EE503. Okay? Some more minutes. Allow me to have a good cut. So anyway, for your special purpose ADC, please don't fit all the parameters just like the commercial part. No, too much. You only focus on maybe 2 or 3 good enough. So allow me to show you many kind of parameters. For example, resolution, LSB, offset, error, gain error, absolute accuracy, relative accuracy, angle, ENAB, okay. Yeah, I mentioned already, you don't need to fit all of them, but you need to understand all of them. Okay, sometimes this one is the most important, but for dynamic operation, especially for high frequency operation, usually we don't focus on INL. We focus on what? ENAB, effective number of bits. But even for ENAB, you have quite many definitions to get your ENAB. Okay, according to what? Maybe according to your INL, maybe according to your SFDR, your THT, your SINET, blah, blah. Okay, so I will tell you in detail. Hopefully, you won't get any kind of misunderstanding for your future, not only design, but also bargain. Yeah, you can bargain the cheap price with your upstream customer or downstream customer. For your upstream, you need to raise the price. For your downstream, you need to increase, because you would like to sell your chips to your downstream. You need to increase the price, right? Anyhow. Resolution. How many number of bits you design? Oh, that is a silly issue. You can say, hey, look, I designed a chip with 14 bits in output, 16 bits in output. Okay, that is the nominal resolution. Because the resolution from the beginning is decided by the designer, so you don't need to measure it. Without check, oh, you have 14 bits for our configurations, your resolution is 14 bits. But it means nothing. We focus very much on effective resolution, not the nominal. Okay? Yeah, for nominal, you can, even after you design your chip, from the beginning you have 16, right? You have 12, then you can have extra 4 bits to be tapped out. So for the outside world, you will see, 16 bits. But you can see 4 of them is not function. 4 of them are not functional at all. Right? But you can still claim, I have 16 bits after packaging, right? So humankind is focused very much on effective number of bits instead of the resolution, the nominal number of bits. It doesn't make any sense. Okay? So it's not important at all. Yeah. So we only measure the effective one. That's it. So in theory, how large is your LSB? If you have n bits, right? If it is ideal, then 1 LSB means the operation range divided by nth power of 2. Okay? That is in ideal. But sorry for that, I told you, after fabrication, each step will be different, totally different from the others. So, for effective LSB, we measure the largest. Got it? We measure the worst case, I mean the largest, the widest step. And then, after you measure the effective LSB, you can divide your operation range by your real LSB. But you can see, if it is ideal, everybody is the same. If it is not ideal, some will above average, some will below average. But we get the maximum one, right? So the maximum LSB or the effective LSB is supposed to be larger than the ideal value. Because this one is larger. So after you divide this by that, in the past, it should be, in theory, it should become this, right? But effective LSB is larger in practice. So after division, the overall value will be less than this. So it means what? The effective number of bits will be reduced. For example, if LSB after measurement is doubled, 2 times larger than the ideal value, sorry for that, you lose 1 bit. So the effective number of bits will become n-1. Okay? That's it. Okay? So the effective number of bits can be measured, but the nominal number of bits, the resolution, you don't need to measure it. You just watch, have a look at the number of output. That's it. It doesn't make any sense. Okay? Got it? So you can guess. This is the very important idea. For the real LSB, if it is 2 times larger than the ideal one, you lose 1 bit. If it is 4 times larger, you lose 2 bits. Okay? If it is between 2 to 4, you lose 1 point some bit. If it is between 1 to 2, you lose 0 point some bit. Got it? Got it? That is the idea. So for ENAB, effective number of bits, usually it is not such kind of n-1, n-2. No. It is always, for example, n is 8 bits, right? After nominally, you will have 8 bits for your resolution, but after measurement, you get 7.5, 6.8, totally possible. But don't offer me some nonsense. Just like, look, I have 5.7, 6, 7, 8. Nobody mentioned LSB, if ENAB in this way. Okay, we round it to make it 5.7, good enough. That is the usual case. 1 more digit after the point, good enough for our ENAB. Okay? Anyhow, some more minutes. How about the offset error? Offset error is here, right? Right? Because from the beginning, 1 step. If it is not 1 step, then we call it, you have some kind of offset error. Yeah, that is the absolute value. Yeah, the transition point here, the first transition point minus 1 LSB. That is an absolute value. But usually we don't how can I say, express such kind of value in absolute. No, in the unit of LSB. So we divide the absolute value by 1 LSB, ideal 1 LSB. Okay? So usually we apply, what is again the offset error? It is 0.6 LSB. Okay? In LSB, that is the idea. So the major difference from absolute to in LSB is divided this or not. That's it. Okay? That is offset error. And yeah, how to make it? The the other definition is you get help from some kind of fit 9. Because for the first definition, you only pay attention to the first break points. If you would like to get help from all the others, then a better definition is to use a fit 9. Then the crossover point here, right? Minus 1 LSV, that is the offset arrow. But never mind you understand it or not, it is not important at all for most of the applications. Okay? Again, I want to highlight that offset arrow, never mind, it depends on only the first breakpoint or all of them through fit 9. I don't care, I don't mind, because usually it doesn't matter. Okay, for our own practical design. And that is from the beginning. How about to the end? We have the so-called gain arrow. Gain arrow, actually, the slope in theory should be 1 to 1, right? But if it is not 1 to 1, you will get gain arrow to the end. Again, not important at all for most of the applications. Okay? Yeah. Never mind for gain or offset errors. If you would like to get better value through the help of fit 9, you can consider, or you can take all the breakpoints into consideration to decide how much offset error here, how much gain error over there. But anyway, anyhow, they are not important at all. Okay? I mean, for usual applications. They are only important for references. For example, if you go to the market to buy fish, or you go to some kind of luxury store to buy gold, silver, or some kind of precious stones, 贵重宝石, right? Oh, offset arrow, gain arrow, it doesn't allow, right? If you have 0.5 kilogram for offset, the sellers simply cheat you to get more money from you. So for such kind of reference standard, they cannot have any kind of gain or offset arrow. Except for that, usually we don't care. Okay, so how about my ADC? This is my smartphone, your smartphone. Even this is iPhone 6 Plus, I guess. Okay, we have millions of this model, right? For each one, if I speak to 10 of them, I promise you, the output won't be the same. Why? Because they have different offset, they have different gain. That's it. Okay? So, are you unhappy? No. What is the consequence? Yeah, just use your mobile phone to record my voice. Everybody of you record my voice. After that, you play back. If your ears are sensitive enough, you will see the major difference is the magnitude is not the same. Okay? With your ADC, with your deck, in your smartphone, after recording and playing back, I promise you, nothing will be the same. If you get out the MP3 file, compare byte by byte, one sample with the other, I promise you, almost no sample will be the same. I mean, from different mobile phone to the same voice. But do you care? No. Only if you listen to my voice, you can fully understand what I'm talking about. You will be happy, right? Not only me, according to the songs online, you download the same songs, right? The same content online, and play with different mobile phone, you will still get different result. But will you be upset? No. Only if the quality is good enough. That's it. Okay. For example, for the first mobile phone, yeah, the ENAP is 20.1. For the second one is 19.9. They are not the same, but the quality to human ears are about the same. Who cares? Okay. Anyway, gain error, offset error usually are not important. Okay. Only for references, just like scale in the market, 秤子. Okay. Anyway, otherwise, not a major concern. So we are talking about the absolute accuracy. Again, for the same input to all the ADCs, I promise you, the result are more likely to be different. So it means what? You will get a lot of problem for such kind of absolute accuracy. For new designers, they will have, they always hope with the same input, never mind how many ADCs you fabricate, they need to get the same output. Forget about it. No, it's really hard. Okay, but again, they are not important. Absolute accuracy usually, again, is not important, not a major concern. Okay, unless you have such kind of scales to weight the fish or your precious stones, your gold, or meters. Okay, how large the room is, because you need to buy it from the market, right? If something wrong with the meters, then you need to pay a lot of money for that. It doesn't make any sense. So we only focus on these references. Otherwise, we don't care about absolute value. So we care that, oh, if you would like to get absolute accuracy, then you need calibration. That is the only way. Nothing else. You need calibration after fabrication. Otherwise, you cannot ensure your absolute accuracy. So humankind only focus on relative accuracy. Okay? And how to measure your relative accuracy? RNL. That's it. Okay? That is the most important parameter for your data converters. Yeah, so we have DNL, we have RNL later. Yeah, 2 weeks later. I will explain in more detail. Okay. Yeah. No more. Again, I sacrifice my time. Hopefully, you can learn more. Thank you.